Alright, looks like I hit the button, so I guess we're committed. So more of the same, I suppose. Let's see how it goes. Having kind of a crappy morning. Happens. Just off. So let's see if I can do this without screwing up somewhere. Anyway, it looks like we have volume. So that shouldn't be a problem, hopefully. I keep my eye open. Let's see. Which one do I want here? I want paradox explained. Yeah, that's it. Yeah, not explained. All right. So the Ian Gostling thing is he's doing this, these are, sort of instruction videos. So in my opinion, you should be kind of careful about what you're going to say because you can mislead people pretty easily. And, this is garbage. It's an instruction regarding anything real. This is my way. I didn't notice that was going to be a problem. Got a new chair. Yeah, it's a little bit of a problem. It's always something. All right, so I guess we'll just play some of this. All right, so he's again. It doesn't matter. You make a video, you make an argument, you make a point, and it just they won't stay on that subject, and so he's resorting to the same old bullshit where he's going to graph a velocity in 2 dimensions. Which is, what's the point? Distance and velocity. Yeah, that's really retarded, frankly, because there's velocity in both of those ideas. You have to have a velocity go with distance and all of that kind of crap. Oh, is this going to work? It's a good question. Let's see. I don't care for it so far. The price of a new chair is making it fit in with the old chair. Fit the space the old chair took. I'd say that's probably almost acceptable. And if I do that, I can probably get by with that just fine. All right. So the circumstance being described. So let's first, again, go through this. You should first premise your argument by saying that you have some reason to reject the simple logic stated that gravity is time dependent. That the reason when you fly through gravity that the faster you go, the less your trajectory is distorted or changed is because gravity is time dependent. It's about how long you're in gravity. So we're back to Newton's basic principle that the first unit of time you fall 1 unit of distance, the second unit of time, 2. Yeah, you fall 3 times that distance. 3 units of distance. And if it's 5, 7, but this 1 to 3 relationship is all you really need to know, because anything, you can just change your unit of time and apply it to anything that moves in gravity. So any tiny amount of distance you could break into 2 units of distance and call, one of them would be the tiny distance and one of them would be the 3 distance. So everything can be broken down into those ratios because that's how something accelerates in gravity. It accelerates at that 1-3 relationship. All right. So to me, that's, it's decisive evidence that, yes, if I go slowly, I crash into the object. I go a little faster, then maybe I can go around once or twice. And if I go fast enough, I'll just be bent a little bit. I can be bent a lot, then less and less and less, depending on how fast I go through the gravitational field, because it's really just about time. All right. And so there's a kind of a simple paradox created in the sense that I can put weight on a scale, on a spring, and I can apply it, at 1 weight at a time. I can just have little 1 masses here, and I could apply a 1 mass to the scale, and I'll get a deflection in the scale of, what I will say, just this much. Doesn't really matter. And I put 2 weights on, I'll get twice that deflection in the scale. 2 units of compression. All right, and the fact is that with those 2 units of compression, I get twice the velocity if I launched one object up. And that means I'll go 4 units of distance. So I put 2 units of distance in. I only lifted this up here, and I only lifted this up here. Now the catch is that when I lift the object up there, I'm doing this speed in the gravity. Okay, I'm doing that in the sense that I can't launch it at the higher velocity, because then I'd have to reverse its direction. Essentially, I'd have to wait for it to fall down onto the object. I've put more energy than is necessary to get to the height if I go twice the velocity. So I have to go at this slow thing where I use a full unit of time. So the time will in fact be the same. The time pushing up against gravity will be equal, because I'll have to use 2 full units of time to get to this location. Because if I shoot it at the higher velocity, I'm going to use 2 units of time per object to get them onto the scale. I'll overshoot the scale, and then they'll have to fall on the scale, which actually will give me back some of what I lost. But let's not complexify the paradox. Alright, so the simple paradox is I use 2 units of distance to create a compression that will launch one object 4 units. And whether I do this as a whole 2 mass, okay, moving 1 distance, or I do it as 2 individuals moving that distance, it's still just the same number of units of distance. I had to move a mass. Alright, 2 times 1 is the same as 1 times 2. Alright. So we'll play his video with that context. He's trying to convert this into some 3 thing. This is somehow took you 3 units of distance to move the 2 mass to the scale. And it didn't take you 3. It only took you 2. 2 times 1 or 1 times 2, but there's no 3 involved. Alright. So he's not even defining the paradox accurately. He's failing to even initiate the video with any accuracy. Alright, so we'll put that back up and play. I mean, it is kind of just tripey crap, frankly. It's just really tedious, you know, that's all you can say. It's tedious to watch these people fail to do justice to the facts. Now, why isn't that showing? Good question. It's on my screen, which means it really should be showing. Alright, I guess we'll just have to find it. It's just really irritating. Alright. So,
the amount of energy it would take. Okay, I'm going to try to explain where I was having erroneous thoughts about this extending the spring and the amount of energy it would take by use of
a trick used by regular conventional physics that's sort of just a bullshit trick. Okay, it's to justify a dopey theory that doesn't work, that doesn't accurately describe reality. Okay, and so it's crap. Yeah.
Work energy graph, but we'll come to that in a minute.
Yeah, where it has time in it twice.
We're going to compare 2 methods of storing energy in this spring. First of all, we're going to do a mechanical extension with a machine or our own energy or force.
Yeah, and if you did it with a machine, it's still only going to be 2 foot-pounds, not 3 foot-pounds. It's just 2 units of mass moving the spring. There's absolutely no 3's involved at all.
We're going to extend the spring down to here and then down to there, which is 2 units of displacement, 2 feet. We're going to mechanically do it and then let the spring go. It does work. And we're going to compare the amount of stored energy in this spring by mechanically extending it.
So it's just doesn't make any sense. The first mass isn't placed up here, it's placed here. and they both have to be placed there, okay, to compress the spring. So however you attach the masses, you're only attaching one mass, 1 unit of distance. No mass has to go 2 units of distance. So it's just bullshit.
To the second method, which is to lift these weights up. One weight will lift 2 feet up to the start position, and it will drop down to here. And then we'll lift the other second pound weight up to here, and it will drop there. Same.
Yeah, no, you lift this weight just one. You just lift the weight, push it right onto the scale. All you need is the 2 mass on the scale. You don't have to lift it up here. You just could lift it from here and just push it onto the scale. Or you could just lift the 2 mass, okay, at the 1 unit of distance, and that's all you need to compress the spring. So you're just lifting from this line. So from this middle line is the only line you need, and you just lift it 2 mass, hook it to the spring, and the spring will take care of it for you. So what he's talking about here is unknown.
Potential energy stored in the spring now, but the work required seems like you're going to get more work out of the spring, because we lift 1 pound 2 foot of distance and put it on. You come down to here, and then we lift this pound.
Yeah, and we just add another pound and no problem. So again,
pound to here, drop it down to there. We've done 2 times 1 pounds of work.
So part of this again is he's just confusing the subject by assuming the spring's compression length is the same as the distance you have to lift it. So obviously you can understand a spring can compress just a little tiny bit. I could have a spring where it's very stiff and I just have to compress it a little tiny bit. It gives me back quite a bit of energy. So he's using an insanely loose spring that needs a long amount of distance to expand and contract, which, you know, again, it makes a mockery of things like a bathroom scale or something. It doesn't need all this space to operate in. But anyway, whatever.
To get to here, and then we've done 1 pound 1 foot, which is 1 pound of work, to get down to here. So 3 foot-pounds of work to get the spring to here. But we should have 4 foot-pounds of energy stored. Well, we have got 4 foot-pounds of energy stored in.
Well, obviously, when you have two mass on a scale, you can't have 4 foot-pounds of mass force stored. So that's just crap. And again, he's just saying that it's 4 foot-pounds because he's measuring based how far it goes in gravity again. I just don't believe that he really has thought about this so little that he actually thinks that I could fly a plane into space much more efficiently, you know, with a big giant payload, going very slowly against the gravity, and that somehow I won't be. He actually believes that this isn't work. So he's buying into a physics, you know, this conventional physics says me holding this does not mean I'm doing any work. I'm doing 0 work because I'm holding it in one position. When you know and I know, if this was 100 pounds, I'd be doing a lot of work to be holding it up against gravity. So, I mean, yeah, it's so obviously stupid what he's saying, what he's defending.
The spring. So it seems like you're going to get more out of the spring than what you put in to extend it by lifting these weights up.
Yeah, and the catch is, okay, to gain the efficiency, you have to gain the efficiency of velocity. So you can't do that. You can't shoot for the small distance going the fast velocity. Can't do that. You can't use small velocity, you can't use the high velocity for the short distance, because then you did put more energy in than it took to actually get to the point you wanted to go to. So you have to essentially, the most efficient velocity is the velocity of free fall against gravity. Because any other, something less, okay, you're being taxed by the 135 tax, in the sense that you're overshot. And then if you use too little, I just did the too little. If you use too little, you're getting very little distance for your work, because you don't have the velocity. And if you use too much velocity, then you've done more work than is necessary for the fall weight you're going to get. How to put that? I didn't say it very well, but the point is, again, just go back to the idea that all you're really doing is lifting a 2 mass onto a scale where it measures I weigh 2, and then you're taking one of the masses off and you're able to shoot it 4 units of distance. That's the real paradox, and he's just evading it with distracting mush.
And you have to lift the first one 2 feet, because this is the position the spring will finish at, where it's going to be released to do its work. So the weight.
So, the position of the spring this is just creating that noise, because it really, you don't have to spatially, proportionally use as much space as you are lifting distance. Lifting distance does not equal spring expansion or compression distance.
Will be here. So to repeat the process, this is where we're going to start from. You would have to go 2 feet, and then this weight 1 foot. That's 3 foot-pound of work.
So there's no 3. It's just a 2 mass lifted 1 distance. The 1 distance creates a weight, which is 2. All right, and the 2 weight will lift 1 object 4 distances high.
4 foot-pound of energy, because it's double the extension. It goes at the square. Double the displacement. The energy goes at the square. So let's work it out. Now along the.
So this isn't working it out. This fake chart making. So he hasn't even labeled the chart properly.
On this graph, along this line is the displacement of the spring, and on this axis is the force required to extend the spring at any given displacement. So as we go along in displacement, we're going up in force required.
And this is completely not true. So this is just an overt lie. It doesn't take more work to compress the spring twice as much. So he's basically saying, look, I put a 1 mass on, it's just this little half a triangle. I put a second mass on, look how much more work the second mass did. Does that make any sense? Come on. I mean, so let's just draw this part again just to be clear what he's saying and just how, he's not helping with crap like that. So, I have the scale. Here's the scale. It doesn't matter where it is in space, really. There's a certain distance. I have to lift it, get it onto the scale. So I lift that unit of distance, and I put a 1 mass on there. So he's got this stupid triangle thing, right? So he says that's this much work, this area. And then I lift a second one and go, let's do exactly the same thing. Exactly the same work. Exactly the same energy put in. Exactly the same. And he says that's equal to this. Okay. This whole thing. Now obviously it's not that much work. I didn't do that much work. It's not extra work in any way. It's just this tiny little triangle is all it was. That's how much it is? Well, that's how much it is. And I just make 2 of those and I make a 2. I don't make a 3. I don't make a 4. I don't make any other number. I make a 2. 2 units of distance against gravity. I worked against gravity for 2 units of distance. My argument is that these are 2 slow times, so I didn't get any velocity out of it. And I'm going to get, if when I launch just one of them, I let one of them fall off, and I launch the other one, I'm going to get 4 units of distance back from the spring. Now this really has to do with dropping things. You really do literally have to use dropping weights. You can't just use mass weight. How much does something weigh? Because obviously when I take the second one off the scale, we'll just go halfway up. It won't give back any extra. But regardless. This is just so stupid. Anyway. Let's play along.
Start here with the spring at rest position. And we're going to mechanically extend it. So as we go along this line, this is the effort line, it's called, or the force line. So we get to
So it's a big lie. Okay, this is so there again, they say this is no effort. This is no work. Nothing. Holding something up against gravity is no work. So as long as I move things, in increments or somehow I don't do any work. If I could use an infinite number of increments of movement, so the movement is so slight and, blah, blah, blah. Well, whatever. I guess there's no point in trying to... It's just as its overt statement right there. They're saying this isn't doing work, when of course it's doing work.
Here we've gone 1 foot in distance and we've got up to 1 pound in force, because the force is obviously going up as we go along. So we've got 1 pound of force, 1 pound of distance. Now the area under effort line.
So this is just a complete denial of Hooke's law. It's saying something completely different, which is twice the mass, twice the work, twice the pressure, twice the. There's no of this, all of a sudden it's 3 thing.
This area, this triangle now, is the work done. The shaded area is the
So that's lifting one mass to the scale.
work done. And you work out the work done by halving this square. If the square length was 2, times 2 is 4, half of 4 is 2. So this is the area of this shape. So from this position, which we are up here now, we're going to mechanically carry on extending the spring. Here we go. More and more force required.
So there's no more and more force required. All I have to do is take another same mass as I lifted before and do exactly the same thing again, and I'll compress the spring. So no problem having to use more energy to compress the spring further. It's just not true.
Force is going up, and the distance displacement is going along as well. We get to here, which is this position from the start, which is 2 foot displacement and a total force of 2 pounds of force. Now this area now, this big triangle now, represents the work done. And let's work that out. Well, 4 times 4 is 16. Half of 16 is 8. This 8 is the work done in...
So I don't even know what the fuck he's doing creating this 8 thing. But whatever.
Mechanically extending the spring from its rest position to here, 2 foot of distance. This 8 is the work done, and also the work.
So there's no such thing. It didn't happen. You didn't do 8 worth of work. At most you did 4, but you didn't do 4 anyway because, yes, it's both lifting jobs will be exactly the same. Lifting a 2-pound weight, 1 foot, okay, is the same as lifting 1 pound and then lifting 1 pound. It's not any different. You're not using more energy to lift a 2 mass all at once, 1 foot, or to lift 2 individual half masses, 1 foot. It's the same amount because it's the same amount of mass in a certain amount of time in the gravity. And that's it. That's all there is. That's what the work is.
Stored in the potential energy formula, which is where this squared term comes in, because this 8 is 4 times the... double the distance is 4 times the 1 distance.
So I don't know how he's going to make this make any sense now. They somehow lost energy. So instead of it being a free energy paradox, it's a huge you lose energy paradox, apparently. He thinks it was more work lifting the 1 mass, 1 unit of distance, than it was to lift the 1 mass, 4 units of distance.
Shows it. Okay, so we've got 8 units of potential energy in our spring now. So let's compare it to the method of lifting the weights up. So the first weight, we're going to lift 2 foot. That's 2 foot-pounds of weight. This is the distance along here. We've got the 2 feet of distance. But the force required to lift that weight...
So again, this has nothing to do with the reality, this lifting distance. You're going to lift them to the same location. You don't have to lift them to some springs location.
Is the weight, what's the weight? It's a pound. So it's a constant pound, this is the pound. It's a constant pound of force as we lifted it up 2 feet. It's gone past the 1 foot, it's gone to the 2 foot now. So this area now is the work done in lifting the first weight to the start position. And then we got, once the spring's down to here, we lift the second weight up just 1 foot. Well, that's a constant force.
So again, there's no 3 units of distance or what. I don't even know why he has a 4 written on here. The second weight does not take twice as much energy to lift to the same original height that the first weight was lifted to. And the very fact that he's saying I only have to lift it 1 unit of distance, how could it be 3 times the work till you lift it 1 unit of distance? So even that doesn't make any sense.
Force of 1 pound over this distance, 1 foot. So we end up with these 3, which is 12. So 12 units of work to extend the spring down to here by lifting.
Let's just do this one more time. I guess I'll try it one more way to say it. It just occurred to me that might make sense. So we get rid of this. And alright, so all you're doing is we're saying when you put a weight, a mass, so let's just take a 2 mass that we can break apart fairly easily. and we take the 2 mass and we set it on a scale. And it compresses the scale 2 masses worth, which will be twice the compression of 1 mass. And twice the compression will create twice the velocity for the 1 mass. Alright. So that's all we do. We just lift the 2 mass up here. We let it compress the scale at the 2 mass level. And then we just put a little lock on that spring. And now we just remove, we have the 2 mass connected, and we just remove one of the masses. Now we only have a 1 mass on the scale. And now we release the scale, and it will give the 1 mass twice the velocity, okay, that the spring compressed at. I guess that would be the trick. The compression velocity of the spring. But regardless, it'll be enough energy to get it to go 4 units of distance high, because of that twice the velocity. So that should be simple enough. There's no 3's, there's none of that exists here. He hasn't solved the paradox. I mean, this paradox is solved by the fact that time is the problem. You can't drop things in 4 units of time and say, I only did 2 units of work, because that's 4 units of work. But anyway, never mind. I gotta say things a little better.
In these weights. So you can see it's much better actually to devise a machine to do it, or do it ourselves with our own energy. There's only 8 units of work. So there is no free energy by lifting these weights up. And this graph shows that. The work energy graph explains it.
Alright, so it doesn't explain anything. He can't do the experiment. There's no way he could prove this is true. None of it, okay? So, because the fact is that twice the velocity going 4 times the distance does not mean 4 times the energy. It just means it was twice the energy. Alright, there wasn't any 4 times the energy because it wasn't 4 times the velocity. It only takes twice the energy to push something twice the speed. And again, they keep trying to defend a truth. They have no experimental evidence indicating it takes 4 times the fuel to go twice as fast, and that it takes 8 times the fuel to go 4 times as fast, and it takes, numbers get exponentially huge. The faster you want to go, you have to start using insane amounts of energy to go that fast. It doesn't happen. And against gravity, the velocity is nothing but a huge, gigantic advantage. The faster you get through the gravity, the less energy you'll spend per mile. At a 1, 3, 5, 7, just imagine you keep extending that. That's your miles per gallon, you could essentially say. The first mile sucks, okay, and then you're at 3 miles per gallon, and then you're getting 5 miles per gallon, then you're getting 7 miles per gallon, so the faster you can go, the higher that number gets.
Quite well. I hope you can make sense of that. Thank you.
Okay, no, I don't make any sense out of it at all.
I'm going to try to explain where I was.
Still premised on the wrong idea that the spring compression is proportional to the lifting distance, which it isn't. You can sort of understand that you could lift something 10 feet and only get 5 inches of spring compression. But whatever. Just really wrong-headed crap. Alright, let's see. Well, there's a couple of little comments. Let's see what the little comment says. Seems fine on this end. Those guys never did any physically gluing. I don't know what that means. Grueling? Anything physically grueling in I guess, their lives, he's saying. Well, they obviously aren't. That's not even true. I mean, you can see the Iron Gostling guy is, kind of in shape. He just, frankly can't breathe. Yeah, I mean, he has some muscles. I mean, he also has a lot of fat, but whatever. So he had to do some work. So he must know some of this by personal experience. But yeah, it doesn't. Why are they? They just keep defending a premise that they ought to just to concede. Well, it is kind of a silly notion to argue about gravity being, time being really important. How gravity works. It's a per second force. So why do you think it's a per mile force? I mean, why does it say 9.8 meters per second of force when it's clearly a per time unit of time force? So why should this argument even have to take place? I mean, I wish they would just explain how gravity works. Just draw me a picture of how gravity works. I mean, I did the linear argument, where you're just rolling something across a surface. And I think I made the perfectly sensible argument that the faster you roll something across the surface, the less pressure it puts on the ground. The less less time gravity has per foot to push into the ground. And if I physically put a scale and then I ran things across the scale at different speeds, the thing would actually weigh less and less the faster I move it across the scale. I mean, doesn't that pretty much prove that, yeah, it's about how long you're being affected by the gravity. The longer you're in it, the more force you collect, the more momentum you collect. And if your mass isn't changing and the only thing that can change is your velocity, well then obviously you're collecting the momentum through collecting more velocity. Really shouldn't be an issue. And such. So I don't know if I want to do any other videos. Just not much of a mood. But I guess, should we see if there's comments? Comments ought to be funny. So we'll do the comments. Yeah. Great job! Blah, blah, blah. It's complete crap. Oh, no comments. It's only 5 views. Okay. It's only posted an hour ago. Too bad. Let's see if I refresh it, whether there's any comments. Still none. Let's just check the newest first, just in case. Okay, nobody. Alright, so we can't do much with that. So I guess we'll go find some other crap to comment on. So I did see a couple of videos that were semi-interesting for different reasons. Like looking. And so we can talk about them. But of course they all have ads on them. It's funny how everybody resorts to this, and I don't know why. I mean, it's 10 cents. Alright, so this was interesting. Yeah, running a train one way on a track, and the track doesn't have friction with the ground, so it actually moves the track. Instead of the train moving, the track moves, because you've put the entire track on wheels with less friction than the friction the wheels on the track have. So that is an interesting bit of junk. I think there's other interesting bits of junk. So we'll just play through some of these. There's the slow motion. So the train is going very slowly, and this is almost moving faster. The track is almost at a higher velocity. I should check this. Yeah, you can see that. Probably have to reduce the sound a little.
Στη διπλανή εικόνα φαίνεται το σύστημα βαγόνι άνθρωπος που αρχικά...
Yeah, it's not exactly the right language, so I guess we'll just do without volume. Yeah, I guess that's what we'll do. So anyway, but yes, the images are good. I don't know what exactly was this. I don't think they did this experiment, so we'll just play it through until the images change. So I guess this is a drawing where the center of gravity is, maybe. I don't know what these dots would represent. Obviously, this is what they're saying, the card's center of gravity without the person on it, and this is where the card's center of gravity changes to with the person on it. So depending on where you place the mass, the center of mass of the object will change, and therefore the distribution of the mass on the wheels will change, blah, blah, blah. There should be more. Guess I could use this pause, but I'm going to smoke. It took a long time. It's still going. It is playing. I mean, it's just taking its time to get to the important... Oh, no, it's not playing. My bad. So we just wasted a big pile of time. The very important time. Oof, it's terrible. Shocking. Alright. Oh, another fucking commercial. You know, the video has 800 views. I mean, it's just pathetic. Fan cart and contest. This is a good one. So the fan's blowing out, and so he's blowing it into the cardboard, and obviously it's you turning the energy, and to some extent it's doing it free enough where you still retain enough energy from the fan to move the whole fan in the box. Now obviously if the box wasn't there, the fan would probably move faster in the opposite direction, but you're still turning the energy almost for free. So it's an interesting fact that you can change the direction of momentum pretty much for free, depending on the mechanism you use. So it's not going that much. It does accelerate a little faster, so you can see it's a slower acceleration, much faster acceleration without the box. So they did lose some, but if you used a U-turn, an actual, like a curved piece of, well-constructed half pipe or something, you could have maximized the turn and gotten more of the energy to cooperate, to efficiently change direction. So this one is just blowing sideways, obviously, because he doesn't have the box the other way, so he's just blowing into a hard surface and everything's going sideways. So, doesn't say much. This is sort of the air track example where you could just argue that, yeah, depending on, how you exhaust this energy, if the fan had wheels in both directions, you might be able to detect an unevenness in one side or the other. So any extra force against the pressure on one side would cause it to move sideways. So it's real energy going in those directions, and any imbalance in that energy would cause motion. So plenty of energy. Now again, conventional physics says no work is being done. So even though we know the fan's running, we know it's using electricity, it's not doing any work because nothing's happening. Yeah, so it's kind of silly. And again, this could also represent detecting heat. So you can have a circumstance where physics will say nothing's happening and something's getting hotter and hotter and hotter, because they don't think of heat as being a direct form of a use of real energy. You have to use energy to make heat. It isn't a byproduct, it is the product. And it's product you've lost to the wrong direction. So in a sense, this could be metaphored or analogized to a heat loss, because you've lost the directionality that you thought was purposeful and functional, and now you have the energy going in directions that aren't functional. I mean, heat can be understood as what things have. When a car goes down the street at 30 miles an hour, you could say the car has heat. in, that direction. It has 30 miles of excess heat in that direction. It's moving. Then in the opposite direction, it's really just heat. It's energy moving in all the same direction. When energy goes in the same direction, we call it motion. When it doesn't go in the same direction, we call it heat. That kind of thing. Seems a little almost like they're trying too hard to demonstrate this one when it was kind of obvious. So I wonder why it has English in it when it's not, the voice isn't English. Momentum of the system fan air cart is 0. See, they say the momentum is 0 when obviously there's a lot of stuff still moving. There's a lot of momentum going on. Okay, it's just not moving the cart with any momentum. But there's lots of momentum in the air, and that's why it could move the little thing. So it's just silly to say there's no momentum. So another variation, I can't remember what this was. So we'll just play it and be a surprise. Let's see what it's going to be. So I don't remember. Oh, he's just trying to show that the air pressure, see, this is the same as the original cardboard box, so he's not really showing the blowback pressure here. The idea the air is going in and coming back out again because it's hitting this wall. So you really should hold this up here because this is probably where all the work is being done. And we could argue it's being done at a point where it has more leverage. Yeah. Hold it higher. There you go, a little higher. So. Alright, so I don't know why he's showing the bottom. I don't think there's any, I don't think in that example he had much air going through the bottom. So it was all going up through the top and flowing, changing the direction. And the more efficiently you change the direction, the more you'll conserve the heat in one direction. Okay, the motion in one direction. Alright, standard stuff there. Elastic collisions are a little complicated, just because you have to recognize what the spring's doing. So the spring compresses. When you bang two things in with springs, okay, this isn't elastic like steel. This is elastic storage. Steel is elastic because it's hard, and it allows for the transfer through the metal. If the acceleration is the right rate, it can perfectly efficiently transfer the energy. Springs store the energy and then give it back to both carts. So that's the trick. You have to recognize the spring when it compresses doesn't differentiate. It just says when I'm going to expand into wherever the lowest pressure is. And so it ends up giving the little cart a higher velocity because when the two things hit, if there were steel, it won't get any higher velocity. It'll just go along with the bigger cart. The bigger cart will lose momentum. The smaller cart will gain the original speed, velocity of the first cart. And so it'll appear to be going faster, but it's just like the bowling ball losing energy to bowling pins. The pins aren't really flying away from the ball. The ball's not moving as fast. The ball slows down. The pins aren't going faster then. And so these can all create some illusions. But the idea is when the two carts hit and you compress the spring can give the energy back in both directions. So the little thing bounced back because it couldn't give its high velocity to the other cart. So it stored some of it in the spring. The spring gave the cart a little extra energy from the total that it would have been if it was a hard elastic rather than a storage elastic. So the two elastic conditions have to really be distinguished, as I said previously. It's unfortunate that physics doesn't make that distinction. They call a spring and they call a hard surface, they call both those things elastic. and they're really not the same kind of elastic. They're not elastic for the same reasons, and they don't do it with the same efficiency. So the sticking together one is the obvious. He just showed you losing a ton of energy. So this is the lose a ton of energy experiment. Okay, but they won't show you how it actually lost energy. So right here we're gonna oh, this is the heavy cart into the light cart. This is the you're still going to lose energy. So you're going to turn a 2-mass cart into a 3-mass cart, and the 3-mass cart is going to have a diminished velocity, and therefore it's going to be going slower than the 2-mass cart was going, and therefore you're going to lose kinetic energy. And they're going to claim, oh, there was a bunch of friction and sparks and all kinds of terrible, awful things happened. That's where all the energy went. But they'll never measure the heat or the losses. They'll never show you any of those as being real losses. You're just going to lose a big pile of energy. So this cart will have a certain amount of energy. The resulting cart's going to have less kinetic energy by their kinetic energy theory. These are visually interesting oscillators. So when the energy is the same from both sides, the oscillator is sitting there oscillating with two different kinetic energies on the two sides. And it's still oscillating because the fact is it has the same momentum on both sides. So this is the uneven oscillator, where you put the energy in just one direction, and you'll see the energy keeps going in that direction. So he's going to initiate it in a direction, but it's against a stop. The stop's going to turn the direction. And it does it again very efficiently. So again, it's another example where it shows you can have momentum in one direction, and for almost no cost, almost for free, you can change it to the opposite direction. For free. Kind of like changing photons' phase. You can sort of do it for free. So the energy just keeps going in the direction, but it's going in that direction by stopping and starting, by accelerating and decelerating. So this is the argument I've used to sort of as a way of understanding why drag can be overcome. This would be a mechanism for overcoming drag in fundamental elemental particle physics. So he just has springs. I don't know why that didn't work. Anyway, he just has springs attached to the two sides, and so just puts energy in one side and lets it oscillate. And then he's just showing the heavier it is, the slower it oscillates. So not a big surprise. And again, he could just drop that weight and create less energy in the system. So by their physics, he can have the oscillator. He can just drop the weight and he will decrease the amount of kinetic energy in the system. But he won't explain how that happened. Another commercial, amazing. And they call it physics experiments, I mean, it really shouldn't be 99.99% commercialized. You think you would do some physics experiments without, if you're going to call your channel physics experiments, it wouldn't be some I want to make money deal. But anyway. So these are rather good Newton cradles for, cheap variety. Work pretty good. So, yeah, so all of that is interesting, but again, it really doesn't get to anything because until we change the masses, we're not going to have the differential. Kinetic energy and momentum would argue the same thing took place here because you can have energy conservation because you haven't changed the masses and therefore changed the amount of the velocity proportional to the mass and therefore made the squared thing happen. So it all works out, but it doesn't work out if you could do this simple Newton's cradle thing with uneven masses. But the catch is that pressurized vessels, hydraulics, and the lever allow you to do the conversions between uneven masses. And that's what all these, it's what 2 years of this conversation has been about, and the defenders of the conventional crap will not draw a lever and explain how it works. Nor will they draw a hydraulic cylinder and explain how it works. So that was a pretty good one. I mean, that stays stable. It must be made of pretty good, pretty heavy steel. I wonder if you made them out of titanium or something, whether that would make a substantial difference. Or if you lead filled them or something. Who knows? So that's a good one too, because it's oscillating. It's got two different oscillations in it. This is the standard shoot a tennis ball. So this is sort of the gun experiment. Now it would be interesting if they actually calculate the difference, because some of these combustion related, so this is kind of a slow combustion, frankly, lighter fluid, compared to some other kind of volatile fuels. And the real interesting question would be is how much extra energy do I give the tennis ball by having this side open versus closed. And then go to the example of the bullet and the gun, and you can make some arguments that the explosive in that case is so fast that it really doesn't matter whether the end is sealed. Bazookas work fine. Their end of the gun, they're a zip gun, a bazooka. All the exhaust goes out the back end. There's nothing to stop it. So it has very little recoil. The only recoil is in the rifling to cause the projectile to spin. So the only recoil you feel is doing a little bit of work to convert some of the velocity into angular rotation. But other than that, and if they actually sealed the back of the bazooka, it would probably just knock the guy down. You wouldn't be able to survive shooting the bazooka. So, it's showing you, one side goes that way, one side goes this way, but there's no qualitative measurement, so we don't get to actually see the calculations that say we have the same energy going one way as we have going the other way. Because it's probably not exactly the same. So they always draw it as if it's a perfect circumstance, and it's not really perfect. You can screw with it a lot. So same deal again. So this time it does look like it's not open at the end, but it's opener. I don't think we're going to see the explosion. Yeah, maybe we are. We're going to see it come out the back end. So these preliminary part, swirl the lighter fluid around. When I was a kid, we used to make these out of tin cans. You'd take 5 tin cans and cut, and we'd make the cannons, and we'd actually have wars. So it was kind of funny, ridiculous, silly, but funny. I mean, we didn't worry about all, we were holding the thing, and you'd light it right next to you, so if it ever did blow up, it probably wouldn't have been a good thing. But it's aluminum cans. How much trouble can that be? Alright, so nothing came out the back. So it seems it's the same as the other experiment. You just did it from a different direction. So it didn't add much. This is the magnet thing. This is, this really is interesting how you can take advantage of how much, you can only do it once because, the magnet will push the thing into the other thing, right? I mean, the magnet will pull the ball into with a, great deal of force. Well, it's not a great deal, is it? You can hear it. But you have to use a lot of force to pull it apart again. So it's a one-time, something you can only take advantage of once. But so the ball comes in pretty slow. The neodymium magnets pull it in really fast. And so you get to shoot the end ball with a lot of velocity. So it's another way of doing a conversion. So, just so much more that you can't even barely see. It's just a blur in the film. It's actually two balls moving. Let's play it again. Oh, look at this silly Tesla thing here. Physics experiments. Oh, Tesla. Not a good example. Now, I still didn't pay enough attention to see whether it was 2 or 1. I think it was only just 1. So anyway, so then the speed of the ball increases on the left because part of the magnetic field's energy is converted to kinetic energy. So it's converted to momentum, frankly. It's not, there is no kinetic energy, blah, blah, blah. So that's it for that one. So they were decent. There was 20? I don't think there was 20 demos in that video, frankly. So I think they lied about that. Yeah, it's the same video. Why is it, well, I guess they can play ads at the very end. The last second he plays another ad. Yeah, that's really funny. Well, it's not funny. It's tragic and all that crap, but, some tragedies are funny. Anyway, alright, so see if there's any better comments, and then we'll do something else if we must. God, I have just no enthusiasm today. Yeah, it's down here. Alright, let's see. In your idea, it's not just mine. Let's see, I am defending the observations of Galileo, Descartes, and Newton. So they're not just my observations. All right. In your idea that when the two mass weight the spring is released against the one mass, how high does the one mass go? Well, the fact is that it's going to leave, okay, with two masses worth of a compression. So it's going to leave. Say if we were using 9.8 and then 19.6 is the numbers, right? To match gravity. So I put one thing on, it weighs 9.8, and I put two things on, now it's going to weigh 19.6. And so the fact is that it's going to have the velocity of 2 times worth of gravity, 2 units of time, and it's going to go 4 units of distance. So yes, it's going to achieve the free fall velocity necessary. Okay, what the same object dropped from the 4 height, it will have that velocity. So it will gain the 19.6 meters worth of velocity. Alright, I think that answers your question. If the one mass takes 2t, there's probably not going to be a context to that. To go the 40 in distance, you're saying. So twice the time to go 4 times the distance. That's how it works. You go twice the velocity against gravity. It's only going to be twice the work because it's only twice the time in the gravity. Then it's equivalent to 2 mass taking 1 time. Right, so how are you going to get the 2 mass to the 1 time velocity? You'd have to use 4 times the energy to get the one mass to a velocity where it can take that whole distance in one time. All right, because it can't go that fast. You have to go twice as slow. Go 1D because it's all about time. It's all about time in the gravity, and a 2 mass is going to experience twice as much gravity, obviously, as a 1 mass. I mean, whether you multiply 2 times 1 or 1 times 2, it's the same answer. Hello there. Interesting video. Definitely having a levers would give you better experiments. Definitely having a lever would give you better experiments. It's all having it constructed well. And as I've pointed out, I really don't have the space to do any of these experiments really well. And they should be done well. Now, I can do them to my gratification or satisfaction, so I will say I have done some of them to my satisfaction. I mean, I did the ballistic pendulum thing with steel bars, and it, proved the professor. I didn't get the Professor Lewin outcome. So I've done various ones of these experiments, but they should be done decisively. And so I have been reluctant to, actually do the one, because frankly, I think I should be able to persuade people with the theory. The theory that that's how the lever works, right? I mean, this simple argument that I can put a 10-ton train going 5 miles an hour into a lever, 1 unit of distance from the fulcrum, and 2 units of distance from the fulcrum on the other side, I can put a 5-ton train, and it will leave at 10 miles an hour. The fact that that will happen, I'm almost arguing I shouldn't have to prove it. You should understand that that's exactly what makes levers. That's the advantage of levers. That's the mechanical advantage. If they didn't do that, then nobody'd be talking about how great levers are. That's what makes them great. The idea that it only, the 5-ton train only leaves with 0.4 more velocity, it doesn't make any sense. So it's almost like I shouldn't even have to make the argument. I mean, the very fact that they don't have any physical evidence showing it taking 4 times the fuel to go twice as fast, or 8 or 16 times the fuel to go 4 times as fast, or because these numbers get exponentially big. There's no evidence of that, and that there's clear evidence that NASA is perfectly aware of how taxing gravity is, and it wants to get through it as fast as it can. I'm trying to understand the paradox involved in releasing the 1 mass from the 2 mass weighted spring. Do the KE folks say the 1 mass does not go forward distance? No, of course they're saying it goes forward distance. They're saying those units of distance are the same units of distance. So that's 4 times the energy. That's their argument. They're saying twice the velocity is 4 times the energy. So if I take a 1 mass and I move it twice as fast, I need 4 times the energy to make it move, and I'll get 4 times the energy from something if it hits. So if I can make a 100-pound person go 50 miles an hour, I'll get twice as much energy than if I make a 200-pound person go 25 miles an hour. They don't think those two things are equal. They think the light guy going fast is twice as much energy. That I could have 2 guys, 2 sumo wrestlers on one side, okay, that are going to be, I have to make sure I say it the right way. I can have one guy, one 100-pound guy. See, I can't equate pulling power with weight, so that won't work. But it's a 2-to-1 thing. They're saying 2 10-ton trains going 5 miles an hour would be a tie in a tug-of-war with a 5-ton train. So I could have a 5-ton train going 10 miles an hour, and the pulling force of that is enough to equal 2 10-ton trains. So that means 20 tons, going 10 miles an hour. 5 miles an hour. So, that's how ludicrous it is. And again, it gets worse and worse the further out you go. So I can go to a 1/4 And, then they're saying it has 4 times the energy. So I could have 4, 20-ton trains. And I could have 8 20-ton trains and just 2 5-ton trains. That kind of thing. I can just keep doubling it and increasing the velocities. All right. They really think the bullet has 1,000 times more energy than the recoil of the gun. 1,000 times. So they don't think 1,000 people with 1 pound of pressure or 1,000 things weighing 1 ounce is the same as 1 kilogram. That kind of thing. All right. Let's see. I'm trying. Okay, we did that. Oh, it's James again. Ugh. The direction of momentum can't be changed for free, says you. So again, you just keep doing these declarative statements. So what should I do about that but block you? I just showed an example where it was almost for free. I mean, the spring and the air cart, right? I mean, it went in this direction, then it went in that direction and completely changed direction and didn't lose much velocity. So you're saying something, and yet you won't produce any counter-experimental evidence demonstrating that what you just said is true. I would argue that it's for free. If I take and I put opposite magnets on a cart, and I move the cart into an opposite magnet, on the wall, okay? So the 2 repulsive magnets are pushing against each other. That the magnetic spring is so efficient that I will, in fact, completely reverse the direction for free. I'll have exactly the same momentum I had this way. I'll still have it going that way. So if you make another declarative statement without any evidence, then I'm going to block you. You'd understand. I've given you 3 or 4 warnings now. This is all you do on this board is type this crap for what you have no evidence. You have no argument, you have no explanation, you have no illustration, you have nothing, but you're some fucking kind of God and you can declare the truth? Fuck that. Argue the truth or get the fuck out of here. Alright, I like the experiments that the person demonstrated, but it's mostly showing momentum, not really proving KE. You can't prove KE. It's just... because it doesn't happen, okay? They'll never show you taking 4 times more gas to go twice as fast. It's not going to happen because it doesn't happen. All right. Your shoot a gun in a rocket experiment wouldn't work. Okay, so I'm just going to block you. Let's see. Because more momentum would go in one direction. So these are just declarations. So yeah, we're done with playing with you. I mean, just as a rule, right? I mean, I have every right to demand that somebody provide some kind of documentation. If you're going to make assertions, you have to demonstrate it with some glimmer of evidence. Somebody showing up just saying, it takes 4 times the energy to go twice as fast. It takes 4 times the energy. F equals ma. Some kind of crap. That's not an argument. It's not part of the subject. It's not relevant to the conversation. I mean, I'm sorry, but it's just a waste of time to have to keep saying, that's not evidence. You saying so is not evidence. Ugh, people. So obnoxious. I mean, I can't even really imagine I would go on some message board and type a sentence to dispute somebody, where I just make a declaration that I don't have to prove, I don't have to provide evidence, I don't have to provide reasoning, I just say so. Okay, so that caused a lull in the action. So I could play another video, I guess. I suppose I'll do that. can find it. The right one, whatever, blah, 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 blah. Alright, so I did that. So this should be the link. It really is a waste of time to declare something being true with no evidence. Yes, it's waste everybody's time, especially when it's been declared over and over and over again, and people have begged for a piece of evidence, and they just keep saying it's true, but they never show you any evidence that it's true. That's really irritating. Another site that using commercials. This at least has 3.6 views, so it's a little better. Spring pendulum. Let's see why I don't know if I like this or not, but oh, this is really simple. Yeah, so I don't know why I saved it, frankly, because it's so basic and so simple. So first, it just shows that twice the weight, twice the expansion of the spring. So not very complicated. And such. And again, the distance you have to lift to expand a spring isn't necessarily proportional at all. I mean, clearly this scale, I could drop something from this height and it would hit the scale and only move it a little bit. Yeah. Especially this part, right? Because the needle is exaggerated. It's on a lever. So the needle is exaggerating the amount of movement in the actual scale. So if I push down on this scale, I would guess that's almost a pound. Let's see what it says. I think it's a 2 ounce. Yeah, so that would be a pound, would be almost half the movement. Alright, so this isn't terribly interesting. So it'll go to 40, and then it'll go to 43, and it'll just kind of show that yes, the more weight you add, it's twice as much compression in the spring per unit of mass. So 1 unit of mass will add 3, and then 2 units of mass will add 6, and 3 units will be almost to 59. It should be, and well, close enough, 49, my mistake. And then he counts the oscillations, and it oscillates faster with 1 mass, and it oscillates slower with 2 masses, and it oscillates even slower with 3 masses. All not very interesting, frankly. But the fact that the spring can oscillate a long time is interesting. But that's about the only interesting fact. Alright, it's no different than a religious person saying the Bible is real. Well, I don't know if it's exactly the same, but it's, because they're talking out of the authority of science. So they're saying, well, science says. And yeah, that's better than saying the Bible says. But it's not much better. Because science is right about a lot of things. I mean, science says, let's see, I can come up with some principles they have right. I mean, you could even go with like Newton's laws. I mean, they're generally speaking correct. I think they're just poorly stated. Okay, but they're generally speaking correct. I mean, there's not an opposite force that causes things to move in opposite directions, necessarily an opposite force. It's just the fact that you're going to lose your momentum and give it to something else. So you don't need an opposite force to take your money away from you after you just gave it away. You already gave it away. You don't need a counter force to make you stop. You stop because you gave away your money. You gave away what you had. Alright, well, I'll deal with that one. So he says, you can say springs or magnets are great converters of energy in regards to weight. Seems fundamental. Yeah, I don't know your argument. Yeah, I'm just saying that one has been repeatedly proven. So, that's for most people, that's not in dispute. That a spring, not as efficiently, but clearly magnets are really efficient in terms of absorbing energy and giving it back again in the opposite direction. So the fact that you can convert momentum's direction for free is a fact. The fact that you can also do it at a price is also a fact. I mean, the runner going around a track has to use his velocity he has to diminish his own force to be able to make the change in the direction. So depending on how you're changing your direction, it can cost you a lot of energy to change your direction. But the fact is, there are ways you can change your direction that are absolutely free. You don't have to provide any energy. But yes, it would be... See, it's hard to say that there shouldn't be any dispute about some things because, I would have thought that everybody would agree with the gravity argument that gravity is time dependent. That the only reason why the fast thing is affected less by the gravity is because it's being affected by the gravity for less time. And therefore, it's not moved as much because it's not in it long enough to be moved by it. And that doesn't seem like something there should be a dispute about. But clearly the Gostling guy actually thinks, and Brozo thinks, that gravity is the same. Every foot you go in gravity, you pay the same price for it. There is no fuel economy for going faster. So going faster up through gravity, no advantage. I mean, it's hard to imagine that they actually do believe that, but Brozo said it clearly. So, I mean, they actually do believe it's a per foot force. If I go 1,000 miles an hour into gravity, I'm going to pay exactly the same fuel cost for the distance if I went, 10 miles an hour. They think it's the same amount of work for me to take a 50-pound weight and lift it really slowly, like take 60 seconds to lift it, and then I could lift it really quick. And they'll argue I did exactly the same work. My muscles did the same, I used the same number of calories. And I think you can logically understand now I used a lot more calories lifting it slowly. I did a lot more work. I mean, how can you get that wrong? How can you not understand that? But it's certainly something physics won't tell you. I mean, it's a plain fact, but I don't think there's ever been a physicist that'll tell you, yeah, it's a lot more work lifting the weight slowly than it is to lift the weight fast. So, I think I'm out of videos. There really is so little. You can spend a half hour going through videos, looking and blah, 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 and you get one video for your trouble that might be a little bit interesting. It might be worth watching, actually. I mean, most of them you just say, you get a minute in and you say, oh, this isn't going to go anywhere. They're not going to establish anything as a truth here. So, it is annoying. But everything's annoying, frankly. Just every single bit of life has gotten incredibly tedious lately. I'm just having a bad day, frankly. Happens. the bad day shows up for no real good reason. Okay, 11 viewers. Yeah, it's just a little bit too low. So, well, we'll go a few more minutes to see if anybody has anything to say or anything they wish to argue or blah, 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 blah. It's a shame that it's hard to find more experiments. Yeah, it is. But, the real shame is that the ones that do exist are done badly, like the silly cracker experiment. I mean, even the Mythbusters, you could argue they could have done that experiment better if they just used springs. Why complicate it with trying to find the perfect compressible material? I have to look under hydraulics because I think the truth will be found in some hydraulic experiment somewhere. Somebody must have done the one cylinder moves, 2 cylinders are pushed. Because that one's going to be pretty decisive, I think, in proving the point. That nobody thinks they lost half the energy. If they moved one big cylinder and they had 2 smaller cylinders move, they wouldn't say, "Oh, I lost a whole bunch of energy," every time that happened. No, it's the other way around. They move the small cylinders and they have one big cylinder move. They're not going to sit there and say, "Oh, I lost a ton of energy." Are just not done well. Well, that's the point. Let's see, there's a lot of dishonesty. Well, yeah, the dishonesty showed up in that Professor Lewin thing. So that was really disappointing that a MIT professor would resort to shenanigans to force the experiment to come out the way his math says it should. And he literally forced it. I mean, it's quite clear. I mean, I would argue that theoretically there's no chance that the experiment can work, and they didn't even bother rigging it by tilting the thing a little bit or finding some more hidden way to distort it. He overtly just distorted it by putting blobs of clay on it. I mean, it was so obvious a distortion. If you compress a spring and release it on a 2 mass in space, let's say it has 1V. Okay, if you make the same compression on a 1 mass in space, KE folks would say it goes at twice the velocity, correct? Yes. I mean, I guess I'm just saying, how could they deny that? But I'm saying that obviously Brozo says it goes 1.4. Twice the compression is yeah, he says, he actually did the experiments where he did twice the compression and he couldn't get something to go twice as fast. So he used the same size object and he couldn't get twice the speed. I mean, you're changing the mass, so I mean, I have to change the scenario because you're changing the mass. So I have to think about what you're saying. Yes, the 1V goes twice as fast. Yeah, he couldn't make that happen. So Brozo claims that doesn't happen. It doesn't go twice the velocity. Half the mass won't go twice the velocity. But yet I don't know, I think they will concede that if I put it on a spring and shoot it through gravity, it will go twice the velocity. So it'll go 4 times as high. So I don't know, there's a great contradiction in what they're saying. I mean, somehow when I'm shooting it sideways, it's 1.4, and when I shoot it up, it's 2. It's twice the velocity. I don't know. Yeah, so, well, we'll see how the hydraulics goes, if I can find some hydraulic experiments. I mean, unfortunately, they're going to be trying to prove something else, or they're going to be trying to do something else, and I'll just be able to use it as an example where, like the Mythbusters, where it actually does demonstrate the kinetic energy myth, but it wasn't what they were trying to demonstrate. So it's not going to be titled, proof there's no KE. It's not going to, it's not going to have the title that I would like, so I'm going to have to find it even though it's titled something completely different. I mean, Brozo proved you can do the lever experiment. I mean, he did it with the billiard balls, and frankly, you just do that experiment more and more precisely, and I think you'll have the evidence, and it'll be pretty conclusive. So, it's like he had the experimental setup that was, 80% of what you need, and he's just got to fix a couple of, the balls do tend to slide sideways. When a lever's pushing, it ends up, it's trying to push it straight, but there's a little tiny arc to the movement, so it does push it a little bit crooked. Little things like that you have to account for. So I did try to get the, whatever his name is. I didn't hear back from the Minute Physics people, so I guess I'll have to harass them for a reply to my last comment and see if their final statement is nothing. And then I'll make public what they said. And how they're cowards. Really, but anyway, the Wolfram guy, because he has a whole paper on Leibniz, and by paper I mean, 10 pages or more, going over Leibniz's accomplishments in his life and all that kind of crap, and it's a very positive statement about Leibniz. It's defending him against Newton, in terms of stealing calculus. Talking about the fact that he did make a calculating machine that was pretty amazing in terms of it using binary math, which was, pretty innovative. But none of this can be sourced to Leibniz actually inventing anything. So Leibniz was a little like a Tesla. I think he just read a lot of other people's work and made better use of it than they did. Just a fact. And but he doesn't go into Leibniz's whole fanatic religiosity and whatever solitons and monads are and all of that kind of crap. And he doesn't really go into the reasoning why Leibniz believed in mv squared. And he doesn't really describe accurately how decisive he was defeated in that argument, that nobody accepted Leibniz's statement, except fringe cult member kind of people. I mean, he decisively lost that argument. In his lifetime. Which I probably will end up doing, is decisively losing in my lifetime, but I will win in the end. Where Leibniz did so based on poor reasoning, I will win based on good reasoning, which will eventually show up, as it always must. It really should. I mean, you can't really perpetually maintain idiocracy, I don't think. There has to be a point where the, things get so ludicrous and stupid, that the advantage of intelligence becomes a huge advantage, and it basically eventually seizes control and corrects all the misdirection created by the stupidity. Alrighty then, I guess we're winding down. Somebody has something to say, or else I shall wander off. Yeah, well, there's new experiments. If they're just going to keep doing experiments that don't mean anything, I mean, let's see how many times we can swirl the pendulum, or let's see what, all these experiments don't have anything to do with the subject, frankly. I mean, the tricky thing about levers, right? I sort of explained this before, is the more you tilt them, you completely change the function. So doing this from 45 degrees down is a huge component is up and down. But when you start going 45 degrees to 0, a huge component is sideways motion. And sideways motion isn't motion against gravity. See, this motion isn't motion against gravity. This motion is. So this motion, gravity is storing energy. This motion, it's not storing shit. You're not storing anything in gravity. So it's a huge difference when they take a lever and distort it to huge, angles, and then start an oscillation, because all of this motion wasn't any stored gravity. This motion does not store gravity. This motion does. And all those little details are really important in how you analyze what your expectations are in terms of what something will do. And they don't pay any attention. So it's just like Brozo ignoring the shape of the objects he's dropping into clay and paying no attention, giving it no thought. Were you mostly joking when you suggested all the Leibniz works can be discredited because he believed in monads, etc.? I didn't suggest that, so I'm sorry. I just said that the binary calculator was a great mechanical invention, and he deserves a huge amount of credit for making it work to an extent. I mean, obviously, we never perfected it. But it is just a fact that he probably didn't invent binary mathematics. That was probably somebody else's invention that he found advantage in. So there's no evidence that he invented the binary number system. So I'm just saying that's where it gets catchy, okay? I mean, generally speaking, I will just say, just like Tesla was not an idiot, okay? He wasn't a complete moron. He did make some valuable contributions to science, but it's so exaggerated in terms of the real substance of his contributions, especially in the context that most of them were basically just theft of other people's work. And, he didn't invent anything. He just made it into something you could show somebody. And he really failed to do that with his own ideas. So when you look at what he did with his own idea was this silly notion that you could, stick a stick into the stream of energy that was in the universe already. And you just have to stick a stick in it and you can collect it, a fishnet or something. And that was really dumb because it wasn't accounting for the fact that it's not rain. You can't hydraulically steal that energy. And so, he spent a lot of money burning holes in the ground, with trying to send electricity to France, which he wasn't going to do. So I don't know what you'd say. So I'm trying to be fair, but I'm just saying there's a real badness to the historical record when it makes heroes out of people that really weren't the heroes. That's my only argument. I mean, the guy who invented the radio is really Hook, or whatever his name was. What's his? And he gave it away for free. All right, he's the guy who figured out the crystal thing, you know, the key ingredient to make the damn thing work. And he took nothing. You know, because he was a scientist. He wasn't a fucking, I'm going to patent it and get $1 billion. He didn't even go to court later to try to claim ownership. I mean, you know, you just gave it away. You were just hoping that the truth will be glaringly obvious. I don't know. I don't think that's what I'm doing. I wouldn't be doing this work if I thought that was just going to happen without any effort. But whatever. At least I hope so. Yeah, no, I mean, obviously it's not obviously, it should be obvious now, and it's not. So what you have to get rid of is the idiot part. The bad ideas have to go out. You have to get rid of the religion before the science can even have a hope to flourish. You have to get the poison out of the ground to grow anything. It's not that there's not enough fertilizer. There's too much poison. Okay, there's too much poison, misinformation in people's understanding. And I'd say science is the huge culprit now in creating all this misinformation about wormholes and going faster than light and warp drives and blah, 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 all this baby talk about all this crap that has nothing to do with reality. Well, of course I make a video regarding most of Brozo's videos. Whether I'll play his video or not is, because he's going to turn it into a steaming pile of shit. I mean, it's going to be disgusting to watch. Because you can't just do a video. You can't just draw a lever. You can't just do something simple. He has to turn it into some theoretic production, some pantomime Brozo. You know, he has to put his floppy shoes on and squeak his nose and do all his antics. Make his jokes. Oh, God. He has the asshole all over it. I mean, I didn't watch. I mean, frankly, I just didn't even watch the video where he has text over the whole video. I just said, I'm not doing this. This is too ridiculous. You post a video, say, look at this experiment. Yeah, the one I just put a bunch of text on top of. But again, he promised a week ago he had this thing. Yeah, it's just, oh yeah, ASAP, he's going to post this video because he already did the experiment. It came out perfect, 1.4. He's going to prove that the lever creates 1.4, blah, 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 blah. Yeah, week later, nothing yet, you know. It's all noise. I'm just saying all these people are doing is trying to create noise. They're trying to, do an experiment badly enough to give you a result that's stupid enough where you'll have some kind of doubts about what the clear truth is. And that's all it is. It's all antics. Just like the clay experiments of 1720 that got us into this mess. Well, 1740, 1737-ish, something like that. I'll try researching for a video that I can send a link to. Yes, that's always good. Specifically a hydraulic experiment. Yes, that would help. You made me realize that when I'm carrying groceries, I should move faster so I fight gravity less. Never really thought to apply that. Yes, anytime you're carrying a weight, you should just think about, maybe I should throw it where I want it to go rather than carrying it where I want it to go. You should throw your groceries into the car. Don't carry them, throw them. Get Get them moving as fast as you can, as quickly as you can, and yes, you'll use so much less energy. But then you'll get fat and lazy, so yeah. You probably could use the extra exercise. But it is, I never thought about it a whole bunch either, to tell you the truth, until we started to have these conversations about how it's just fundamentally interesting about how if you could theoretically get something moving really, really fast, like light speed, you could effectively negate Earth's gravity as even being anything at all. It would be such a tiny deterrent to your motion. That it would be just about meaningless as it costing you anything to leave the Earth's gravity. Because you would be 1,000,000 miles away, in a second. 3 million miles away, right? No, you'd be 3 million meters away, in 1 second. And by the Galilean numbers, you've just, you've got fantastic gravity mileage numbers. It's not 9.8 meters. It's whatever 0.0000000000000000. Yeah, it's hard. I probably should think of maybe I can think of some generic thing we do every day. But just that simple argument. Professor Lewin does it in his video. He holds his briefcase up and basically says, look, I'm not doing any work. And says it like it's not a joke. It's like, why would you even try to defend physics that would say that, right? It's such a stupid thing for physics to say. You're just saying, oh, that's not the right answer, right? You don't really mean that, right? I don't think Professor Lewin thinks it's no work. I'm just saying, he's basically saying our mathematical work equation is this retarded and limited. It doesn't have anything to do with reality. It just has to do with, making our math circular. And so it really doesn't have anything to do with reality, because yes, the work really is the time I'm fighting gravity. It's not about how much I move something. Moving something is only part of the equation. The real equation is time in. And just that simple. He could have used that simple experiment as an example and just said, see, this is why gravity is about time, not distance. So the work equation is obviously a pile of crap, because it's clearly about how much time you're in the gravity is going to decide how much you are collecting from the gravity. How long you're free falling. And you can increase your free fall time by doing it in very tiny increments. So the tinier the increment of you fall, just let it fall this little centimeter. And then I let it fall a centimeter, and then I let it fall a centimeter. It'll take me a lot more collective time, because I'll never gain any velocity. So if I can keep stopping myself from getting velocity per unit of time, I'll take a long time to get through the gravity. But I'll also collect a lot of gravitational energy in the thing I keep hitting, the thing I keep using as a stop. But the problem is the stop doesn't go faster either. So the stop can't gain any advantages of velocity. So it can't increase its momentum. But I always knew that was wrong, right? So when I saw that Professor Lewin clip maybe 5 years ago, I said, that's just so stupid. But I didn't think that it's stupid for a very specific reason. And it's stupid to try to defend 1/2 mv squared, because they had to break all the other formulas to make 1/2 mv squared work. So they have to do mgh, height, instead of mgt, time. And then they broke work. Work equals force times distance, when it's really force times the time you apply the force. They had to break everything around this stupid 1/2 mv squared for 1/2 mv squared to survive. They had to make all the other formulas compatibly broken. You plan on streaming in the evening. Yes, you already said this. I don't plan, okay? So I don't know. It seems likely, especially in the summer maybe, that I would do an afternoon or evening, but we'll see. I feel like there would be more interesting discussion. Yeah, it just depends. The morning it's Europe, okay, and later it's America. And frankly, I haven't found America to be any more interesting, than the Europeans. But the Europeans are easy to offend, so it works both ways. So I lose audience because they're easily offended. They're thin-skinned, as they say. I am a creature of habit. I do like routine, so I have had the routine of making these morning videos, and it's just the routine. Have you heard of this plan to deflect an incoming asteroid? Yeah, some of it makes sense. And I think they say using lasers is better than ramming it with mass, presumably because the KE bonus with light speed. Yeah, well, there's no KE bonus with light speed. I mean, it seems kind of obvious that, forces don't interact with forces. You can't move a force any faster than the speed of light, so there is no speed increase possible. Can't double its speed, you can't do anything, so I don't see how that could even be a thing. And lasers are not very efficient, frankly. You need an awful lot of energy, so they're going to have to use like a nuclear bomb to create the laser light, right? I mean, how are you going to store the energy? How are you going to produce the energy in space? Because if you do it from Earth, you're going to vaporize the atmosphere more than you're going to deflect anything. So I don't see how any of that could work. And certainly you're not going to win by shooting bullets at it. Okay? So the idea is you're going to need to hit it with an explosive that has mass. So you're going to you got to hit it with some sort of titanium shell or something. Something that's got some real pushing power. Or you hit it with a nuke. You could say the nuke's a lot of energy. But when are we going to trust NASA to shoot nukes into space? Yeah, I don't know. Are you going to trust whatever his name is with that one? Like Mope. What the fuck's the guy's name? I forgot this Tesla guy's name. I'm glad I forgot some things because they're probably worth forgetting. Musk, yeah, Mope, Musk, it's pretty close. Elon Mope. Yeah, just what a retard. Anyway, ew, creepy. You're gonna let him shoot nukes into space? I don't think so. But whatever. The problem is the ones we can't see, I mean, they've kind of got all the ones, that are visible that could really do some damage, and they got them all tracked, and so we're pretty safe for the short term. But it's the comet you can't see. You know, the comet that comes out of nowhere every 500 years or every 2,000 years. That's the one that'll fuck you up. But I won't be, you know, frankly, if hope could make it happen, you know, I'm afraid I would be, you know, the only real hope, you know, the best hope is the quick, easy disaster that just, you know, splits the planet in two. And obviously I would be a victim like everybody else, but it would be a sigh of relief. You know, the horrible experiment is finally over. I'd be like Ripley in whatever, I don't know, Alien 5 or whatever one that was. You know, when they made the fake Ripley. Well, Musk is just such an unsubstantial person. It's just, you know, he doesn't know any of the shit he talks. He doesn't understand any of this stuff, you know. It's just pathetic. He has no clue about any of this science. You know, he's just a Trumpy. He's got money and power, and that's it. And he's clever enough to know if I'm going to lose money, I'm going to lose somebody else's money, not mine. You know, so he makes sure the deal is, hey, if it works, I get rich. If it doesn't work, you get poor. You know. Alright, well, I guess we're done. So, anyway, this has been a draftphysics.com video presentation. And such, we'll try again as something new or something worthy of comment requires. And I guess I'll just make some foundational videos again, another version of the let's just do this gravity is about time argument. You know, try to make it as short and sweet as possible. And, you know, all the other little lever and hydraulic arguments. And then I'll get back to some of the two-slit stuff. And, you know, the Eddington experiment. And such. So 7 viewers that's not very good. I mean, it went down from 11 to 7, so you know that's a little discouraging. But you know, life on the internet, it's been discouraging for a long time, and somehow I don't get discouraged enough to run away. You know, I'm in it to win it. You know, so that's what I'm going to do. I'll keep rolling these dice. Because I know the good numbers are on the dice. I know they can show up. You win. Those would be the numbers. But anyway, I know I can do it. I just got to do it. Just got to wait for it to be dead. Yes, and I'll have to play a part in didding it. But, yeah. It can only be a matter of time, I think. Because I'm goddamn right. Most all of the time. And they are goddamn wrong most all of the time. The thems. The horrible thems. Alright, so till the next time and such, I'll get out.